Alright, everybody, welcome back. In this video, I'm going to be talking about eigenvalues and eigenvectors. And so, let's start off with, let me write down the equation. It'll be easier to explain. So, I'm going to have a matrix, I'm going to zoom in a little, A, and it's being multiplied by a vector x. And if x is an eigenvector, then it equals lambda times x, the vector, which I wrote kind of ugly. Okay, so let me write out what each variable means. A is a matrix, right? And then x is your eigenvector. And lambda is a scalar, and that is your eigenvalue. And so what this equation means is that this vector x, which we're going to call the eigenvector, when it's multiplied by its a corresponding eigenvalue, it basically equals if we were to take a matrix and multiply it by the eigenvector. And so in order to find the eigenvalue, I'm going to walk through the proof with you guys. Okay, so let's write down the equation I just wrote. A times the eigenvector x times the eigenvalue, and then x. Right. So our goal here is to find lambda, which is our eigenvalue. And so I'm going to start off by moving lambda times the vector x to the other side. So to do that, I'm going to subtract. So a times a vector x minus lambda times a vector x equals 0. And now I could extract an x from both terms. But be careful here because lambda is a scalar and a is a matrix. So you have to have the lambda multiplied with the identity matrix, which is I. And then it's going to be multiplied by the vector. And so from here, this eigenvector can't be 0. So that means this piece has to equal 0. But this is not just 0. This is a vector full of zeros. And so in order to solve this, you're actually going to take the determinant of this matrix, A minus lambda I, and that's going to equal to 0. And so that's how you solve the eigenvalue. So let's go through an example. Okay. Example. I have a matrix A, and what values did I have? 1, 0, 5, and 6. And so let's try finding the eigenvalue in eigenvectors. So start off. We're going to have to take the determinant of A minus lambda I. And that's going to equal 0. So that means I'm going to find the determinant of 1 minus lambda, 0, 5, 6 minus lambda. And set that to 0. And so this is a 2 by 2 matrix. So the determinant here is just multiplying the diagonals and subtracting them. So 1 minus lambda times 6 minus lambda. And then 0 times 5 is 0. So we don't really care about it. And we're going to set that equal to 0. And so each term can be set to 0. Oops, 6 minus lambda equals 0. So lambda equals 1. I'm going to label that lambda 1. Lambda 2 equals 6. And so for this matrix, it has 2 eigenvalues. So let's try to find its corresponding eigenvectors. So to do that, I'm going to take the same equation I had before that I extracted from the proof. A minus lambda 1 times identity times x is, I'm going to label it as 1, equal to the 0 vector. And so the first lambda was 1, x1 prime, vector, the 0 vector. And so, what was A again? Our A was 1, 0, 5, 6. And so that means this is 1 minus 1 is 0. 0 minus 1 is minus 1. 5 minus 1. Oh, no. I did that wrong. I'm sorry. My bad. It's being multiplied by the identity matrix. So that means only on the diagonal it's being subtracted by 1. I was doing that too quick. So let me just write it out, because I also confuse myself. Let me write it like the thing. It's 1 minus 1. This is 0. Does not get subtracted because it's not on the diagonal. And then this is 5. Because, again, doesn't get touched because it's not on the diagonal. And then this is 6 minus 1. And the x of 1, I'm going to put represented as A and B. This is going to equal the 0 vector, which is just 0, 0. Okay. And so you can see that this is just a system of equations. And so, okay, let me simplify it first. This is 0, this is 5, this is 0, this is 5. A, B equals to 0, 0. So, if you multiply, this is 0 times A plus 5 times B equals 0. And similarly, 0 times A plus 5B equals 0. And so our first eigenvector is 1 and 0. Okay. On to our second eigenvalue, which I'm just going to put this aside. So again, A minus lambda 2 times the identity of x2 equal that to the 0 vector. And so our second lambda was 6. So it's A minus 6 times identity matrix x2, 0 vector. So again, this means we're just subtracting 6 from the diagonal of A. Yeah, of A. So I always forget what A is. This is 1 minus 6. This is 0. This is 5. Doesn't get touched because it's not the diagonal. And then 6 minus 6. And I'm going to do C and D, right? Because I did A, B. Okay. C and D. That's 0, 0. Vector. Okay. Alright. Simplify it. It's minus 5. 5. This is 0, 0. C, D. Again, it's a system of equations. So this is minus 5C plus 5D equals 0. And so that's 5C equals 5D, which means C equals D. And so a vector that represents that x2 is just 1, 1. And there you have it. So we have two eigenvalues for this matrix, which is 1, and its corresponding eigenvector is 1, 0. And the other one was, what was the other one? Positive 6. Positive 6, and its corresponding eigenvector is 1, 1. And there you have it. That's eigenvalues and eigenvectors. Thanks for watching.